Hello everyone, my name is Jafari and I would like to welcome you to another video. In this video, we're going to continue learning about data transformation and massaging. Specifically, in this video, we're going to focus on feature extraction. Feature extraction is a series of tools that we use to extract features. And there is no better way to actually explain this because that's exactly what it is. But we're going to go a little bit deeper, and of course we're going to be using examples to do that. All right, let's get this slide. All right, so the process of feature extraction as shown in this slide is basically, regardless of the type of data you have, it could be structured data or unstructured data, you do a series of different things to this data. It could be dissecting it, picking it apart, unpacking it, simulating it, anything you can think of in the pursuit of creating features or extracting features from this data is feature extraction. So there may be different methods, and some of them are heuristic and some of them are more established methods to go about this. I believe the best way we can actually learn substantially about feature extraction is through examples. So we're going to see a couple of examples here together. The first example here, we have one categorical attribute. It's just emails of individuals, right? So we can see, if we look closely, we might be able to extract features from this seemingly information-less attribute. I mean, it's just instead of strings, it's just an email, it's just a name, it doesn't have much information. We might be able to actually extract features that might prove useful for a specific analytic case. I'm not saying this feature extraction is going to be useful for any analytic case that there is email, but it could be useful. For instance, if you want to separate between the people who are from academia or from the industry, that might just prove useful for your analytics. Let's look at an example. In this example, we have the data of 7,500 engines of cars. So these are not 7,500 different engines. These they could be the same engines, at different period of time that their noise data, their working noise data, car engines have been recorded. And we've got, if you pay attention to the slide, it's going to start moving. We've got 1,000 milliseconds of data for each of these data objects, right? So if we were to, take a closer look at this data, we've got that 1,000 milliseconds of data for each of these 7,500 data objects. But we also have a label, and there are 5 possible labels to these engines, right? The engines could be working healthily, it could be suffering from misfire 1, misfire 2, or misfire 1 and 2, and it could also be suffering from valve clearance. So we do know the state or the label of these engines, and we also have the noise data of these engines working, right? So if we were to look at each of these 1,000 milliseconds of variation and noise data, this is what we would get. This is what we would be looking at. You can see there are a lot of oscillation and reciprocations in the data, right? So for the purpose of classifying, we could be going about this data for data transformation in different ways, right? So there are 3 different ways that there are actually more, but there are 3 different ways that we are going to discuss in this video. The first one is morphological, right? So let's focus on the morphological, and then we're going to cover the other 2. So on the morphological means relating to shapes of objects. So when we have a morphological approach, we tend to look at the shapes of the objects, right? So in this approach, we will look at the ups and downs of these oscillations, and we start doing some feature extraction. This is a heuristic type feature extraction. For instance, we say we've got in this data object, we've got 4 peaks. We actually count the number of peaks, 1, 2, 3, and 4. And then we count the number of valleys, 1, 2, 3, and 4, and 5. And then we also count or like measure, calculate the max oscillation in this data object, right? So now we were able to, come to some simple extractions, features from this data. This would make more sense. We actually had done this for, all of the data. We would be able to see them visually, but let's just sort of like think of it as a smaller version of that example. We've got 5 cases. We've got 4 types of faults, and with a healthy situation. So now we were able to come to number of peaks, number of valleys, and max oscillate. We have re-represented the data by only these 3 attributes. We found them morphologically or heuristically. Now, instead of having to deal with 1,000 numbers, we only have 3 numbers. Not only that, these 3 numbers, are capturing things about the data that are more important for us. Sort of like it brings the information that we are interested into the surface, right? So that's the morphological one. And we can also see that, these, seemingly naive and seemingly uninformative features we have extracted here, they're actually showing some patterns. For instance, if this is going to be how fault 2 is going to look like, this is just going to be enough for distinction between this fault and the rest of the data objects for a classification algorithm. Now let's look at the functional data analysis. Imagine we have this sinusoidal function with 9 parameters, right? And we fit this sinusoidal function to these data objects, right? By finding these 9 parameters, we can see that this function simulates this data pretty nicely, right? Not only that, for this specific one, we can see it actually can simulate the other data as well pretty nicely. I mean, it actually can capture the pattern and remove the noise from these data, right? So, instead of us having to have 100 or 1,000 data objects to represent each 100 and 1,000 numbers to represent each data object, we can move to 9 parameters, right? So the parameters of this function that simulated the data pretty nicely could be used as the features of this data that we can use, and now we have been able to transform the data and also bring the information that it's important for us. What are those information that are important for us? These ups and downs, these oscillations, it's the extent of these ups and downs. So all of those have been captured by these parameters. So another way we could go about this is, of course, principal component analysis. We could be looking at all of those 7,500 data objects as represented by 1,000 columns, and we could run a PCA and see how many PCs are going to account for a good chunk of the information data, and use the first few PCs. Of course, that's going to be another approach we can go about this. Let's look at another example here, example 3. In this example, we have, it's going to be a little bit different. So we are going to be using feature extraction in this example for visualization. So we've got the speech DF, which is the content speech of Donald Trump in 2020 and 2021, right? So we've got the content of this speech, the state, the city it delivered this speech to, the date, and day, month, and the year of the speech, right? So we could be unpacking this content, right, as a way to feature extraction, and calculate the number of times these 4 words have been appeared in the Donald Trump speeches, right? And by dividing that number of times by the number of words that each speech has used, we could come to a ratio of word usage for these 4 words, right? So this would be the stepping stone we could be sort of making to come to this visualization. that somehow captures the essence of these speeches, Donald Trump's speeches in each of these months, and if you can see any patterns. They're not, very distinct patterns here, but our point here is to show you that we could also go about, talking about feature extraction from a long string, while calculating the ratio of each word being used there. This is a very simple example of natural language pre-processing, which is basically a very well-developed discipline that has many different approaches for the task of feature extraction from transcripted or written language. So that's natural language processing, NLP. All right, so let's look at the final example here. In this example, we've got the data of 122 countries, and each of the country has been, described by 90 different attributes, which these 90 different attributes are the 9 happiness indices of these countries in 10 years, right? We've got 2010 to 2019, right? So we could be going about this feature extraction again in 3 different ways, right? There are actually more, but we're going to discuss 3 of them here. The first one is clustering, right? So we could be looking at clustering as a feature extraction method. Let's just see how it is. So we just use all of these data as dimension in this data set with 122 data objects and just come to this meaningful clustering, right? What is a clustering? At the end of the day, when you do a clustering, you basically reduce your data from however many attributes it has to one categorical attribute, right? So this is going to be the result of your clustering, right? So this is going to be cluster. Based on what cluster they are at, you're going to, have this new categorical attribute that is basically, the cluster that each of these data objects are a part of. So, in essence, you transform this data by, 90 numerical attributes to one categorical attribute. So that's one way to look at this, right? Another way we could go about this, of course, is functional data reduction. On this functional data reduction, we could look at each of the country and each of the happiness indices of the countries and look at their 10 numbers from 2010 to 2019 from a perspective of a time series and try to fit a linear regression formula here. And instead of having to include all of these 10 numbers, we could include the parameters of A and B, which are the inertia and the slope of this linear regression, right? So you could see that we are managing to extract what's important for us out of each of these happiness indices for each country. So in effect, we are going to be able to reduce this data. We have to have 10 numbers for each of these happiness indices for each country. Now we can have only 2 for each of these countries. So we can reduce and at the same time transform this data. And another way we can go about this is, of course, principal component analysis. And with principal component analysis, it's very similar. You've got these 90 attributes and you run a PCA. For instance, you see the first species account for 71% of the variation, and you use this to say, okay, this is a good visualization. I've got 71% of the variation. I was able to visualize them, and this is data transformation for you to be able to create this visualization. So before ending this video, let's talk about if feature extraction is data transformation or data massaging. Of course, anything that we're talking about here is a data transformation. Any data massaging is also data transformation. But since in feature extraction, we and in all of those examples that we saw, we would be able to do the analysis without the feature extraction, but only we did those feature extraction to be able to create more effective analysis. And we use different tools to be able to extract features, right? I mean, different tools would end with different features, right? I mean, not necessarily there were like one certain way to go about this. So doing feature extraction and finding the best way to do it is basically for the purpose of having more effective analytics, and therefore we can actually call feature extraction by and large as data massaging. Alright, until the next video.